welcome back to my channel. So today we are going to learn about binary search tree. Binary search tree is a type of binary tree. And binary search tree has three types of conditions. The first condition is all elements must be unique. And the second condition is binary is nothing but the root node must have at most two childs. So it means it can have 0 child and 1 child or 2 child. And the third condition is the value of the left subtree should be smaller than the value of root node. And the value of the right subtree should be greater than the value of root node. So let us implement this small binary tree. So let us take 10, 9, 11. So you can see this, it is a binary search tree. It obeys three conditions. The first condition, all elements are distinct. And the second condition, the root node has two children. And the third condition, the value of the left subtree is smaller than the root node. And the value of the right subtree is greater than the root node. Let me discuss some of the operations on binary search tree. The first one is insertion. Insertion. So let us take these elements, and the first element is 11. So we should directly insert the 11 here. And the second element is 4. So while inserting the second element, we want to compare with the first element. We should check if the 4 is greater than 11 or less than 11. We know that 4 is less than 11, right? So we should insert at left side of the 11. Like this. And the third element is 20. So like this we also compare with the first 20. So right here 20, I want to check 20 is less than 11 and 20 is greater than 20 is greater than 11, right? So we should insert 20 at the right side of the 11. Fourth element is 6. Like this we want to check here. 6 and 6. So we know that 6 is less than 11. So we should insert at left side of the 11. So but here already the element is existing. So we want to compare 6 with this existing element. So 6 is compared with 4. I want to check here the same condition. Either 6 is greater than 4 or 6 is less than 4. You know that 6 is less than 4, right? So we should insert 6. 6 is greater than 4, right? We should insert 6 at right side of the 4. And the element is 2. Like this, we check 2 is less than 11 or 2 is greater than or 2 is less than, right? So we should check here also. 2 is less than 4 or 2 is greater than 4. 2 is less than 4, right? So we should insert 2 at left side of the 4. And the element is 30. Like this, I want to check 30. 30 is greater than 11, right? But here there is an element called 20. So we want to check 30 with the 20 also. 30 is less than 20 or 30 is greater than 20. Now that 30 is greater than 20, right? So we should insert 30 at the right side of the 20. And 25. 25 is greater than 11. 25 is greater than 20. But 25 is less than 30. So we should insert 25 at left side of the 30. So like all this, we should insert 8 also. 8 is less than 11, 8 is greater than 4, 6, 8 is greater than 6. We should insert 8 at right side of the 6. This is called insertion. Coming to the deletion, we have three conditions. Maybe the deleting node must be leaf node, or it has single child, it has two child. When the deleting node has two child, so there are two types of conditions: in-order predecessor and in-order successor. In-order predecessor is nothing but the greatest value in the left subtree. In-order successor is nothing but smallest value in the right subtree. So let us delete some elements. Let us delete which element is a leaf node. So can we take 8? Delete 8. So the deleting element is 8. It has no children, so we can delete it directly. Like this. Okay. And the second, single child. The deleting node must have a single child. Let us delete 20. the deleting node has a single child, we need to replace the child with the deleting node. It's really simple. So we want to replace 30 with the 20. So after deletion, the result will be like. So here comes the 30 and it has a child number 25. So that also come to write. And the node which has two children, DB11. Good. So there are two types of conditions as I said, in order predecessor and in order successor. So there are two answers. So this is the in order predecessor and in order successor. We can only have either one of them as solution. So in order predecessor, we are replacing the maximum element with the deleting node. So in this left, so 6 is the maximum element, right? So we are replacing 11 with the 6. So the output will be like this. Or else we can take in order successor. In the right subtree, 25 is the smallest number. So we are replacing 11 with the 25. Or either the output will be like this. And this is known as deletion.
As insertion and deletion completed, now let us look into the search function. For suppose the given element to be searched is 11, it will be considered as E. So we'll go into the function. If root equal to null, root is nothing but the value 11. Is 11 equal to 11? No. Now we'll go to the next condition. Root dot value equal to key. Root dot value is nothing but 11. Is 11 equal to key 11? Yes, true. It will print as key form. Now let us take another example on element key to be searched as 2. Again we'll go into the function. We'll check whether root equal to null. No, the given root is not equal to null. We'll go to the next condition. Root dot value equal to key. Is 11 equal to key value 2? No. Again, we'll check two conditions. If key is less than root value or key is greater than root value. Key 2 is less than root value 11. Yes, again we'll go into the search root dot left. Search root dot left is nothing but we're calling the search function and going to the root dot left. This is the root and root dot left is 4th element. Again, we'll go to here. We'll say root equal to null. 4 is equal to null. No. Again, we'll say root dot value equal to p. Root dot value here is 4. Is 2 equal to 4? No. Okay, we'll go to the value. And if e less than root dot value is 2 less than 4s. Again, we call the recursive function search root dot left. Again, we'll go to the search function. We'll say root equal to null or root dot value equal to e. E less than root dot value. Again, 2 is less than 4. Again, it will go to the left side of the root value. Again, we'll go to the function search. Is root equal to null? No. Root dot value. Root dot value here is nothing but 2. 2 is equal to 2. So the given element is equal to the key. It will print as key form. Now let us take another example to be searched as 20. Again, we'll go to the function. Inside the function, is root equal to null? No. It will go to the condition. Root dot value equal to key? No. Again, it will go to the condition. Is key less than root dot value? Here key is 20 and key is less than root dot value. Root dot value is nothing but 11. Is 20 less than 11? No, right? It will go to the another condition. Key is greater than root value. Is 20 greater than 11? Yes. Again, it will call the search function and these all operations will be done. So now the root value is 20. It will say 20 equal to null. No, it will go to the next condition. Root dot value is nothing but 20. 20 equal to key 20. Yes, it will print as key form. Now let us take the example and key to be found where the element is not present in the binary search. Let us take key as 1. left, root and right. So what this exactly means, will go into the function. In order function. For this binary search string, root node is 11. So first the root node will be 11. It will go into the function. Root dot left not equal to none. Root dot left is not equal to none. So again it will call the in order function. It will go to the function. Root dot left not equal to none. Root dot left is nothing but 2. 2 is not equal to none. Again it will call the in order function. Now root will be 2. Root dot left is not equal to 1. But here, root dot left is equal to 1. Next, it will go to the print statement and prints the value 2. It will go to the next statement and it will say root dot right not equal to 1. But here, root dot right is equal to 1. So, the root will become 4. Root dot left not equal to 1. But here, root dot left, which is already printed, it will be declared as none. So now it will go into the next statement print. It will print the root dot value. Root dot value is nothing but 4. 4. Like this, continuously recursive function is called, and now the in order traversal will be 4. After 4, it's going to say root dot right. Root dot left is none, so it will go to the root, it will print 6. It will go to the root dot right. Here, root dot left is none, I will print root 8. It will go to the root dot right, but root dot right is none. So, this whole part is completed and this whole part is the left subtree of the root 11. So, this all will be considered as none. So, this is the root, it will print root 11. It will go to the root right. Root right is nothing but value 20. And then it will go to the root dot left, which is none. It will print root 20. Root dot right is 30. It will go to the root dot left. Root dot left is none. So it will go to the root 25 and 25 is printed. Root dot right is none. So this part is completed. So it will go to the root 30 and it will print 30. Root dot right is none and it will go to this will be the last element. If you observe clearly, this is in the ascending order. So first element will be the minimum element and last element will be the maximum element. So why we are particularly using in order traversal is it is easier to take the minimum and maximum element.
Okay, now let us see some more basic operations on BST. In that, firstly, let us check whether a given element is a leaf node or not. As we all know that leaf node means in a BST, any node that doesn't contain any child, that is left child and right child, and that is called leaf node. If you look at this example, if you see 2, here 2 doesn't have any left child, similarly it doesn't have any right child. So we can call 2 as the leaf node of the BST, right? So 2 is a leaf node, similarly 6 is a leaf node and 25. These 3 are the leaf nodes of this BST. Now we are observing through the tree, so we can simply say that yeah, this is a leaf node and this is a leaf node. But what if it is given through a program and how to execute this? If I want to check whether that 25 is a leaf node or not. Let us see the algorithm. Now I am declaring a function here. A function with the name is leaf, and I am passing two parameters, root and key. Here key is nothing but the element that we are checking whether it's leaf node or not. So let us assume key value be 25. So here now key value is 25 and root value is 11. Now let us check if root is none. No. So if root is none, no, not at all, because there are some elements present in our BST. So it comes else statement if root dot left is none and root dot right is none. As our root has both left, root dot left and root dot right. So it is not none. And similarly, 11 is not equal to 25. So it comes to self dot is left of root dot left comma key. These both are the recursive functions
that calls this calls the function continuously unless the BST is completely ended. So now the root dot left, that is 4, is being replaced with the 11. And again the same process is being continued. It checks whether it is null. No, not at all. So if root dot left is null, again 4, root dot left is not null, and root dot right is also not null. So again it moves and comes. Now the root becomes this one. Again, now root becomes 2. So it checks again. Root dot left is null. Yes, root dot left is null here. And root dot right, yes, it is also null here. And also checks whether 2 is equal to 25. No. Even if it is the leaf node, it does not match to the key value that we passed. So this is not what the value we are checking for. So again it moves. Now it comes to root dot right. Because of this recursive function that we wrote here, self dot is leaf of root dot left comma. So again it checks to the root dot right. So it comes now root 30 becomes the root value. Again it checks whether it contains root dot left is null and root dot right is null. Root dot left is not null, but root dot right is null. So the condition is failed itself. So again it comes, the recursive function works, and the root value is being changed to 25. So finally the root value is being 25. Root dot left is null, root dot right is also null, and the root value 25 is equals to 25. So the value that we are searching for is 25, and also the 25 is the leaf node of the BST. So this is the way how to search whether an element is a leaf node or not in a BST. Now let us find the maximum height in a binary search tree. If you look at the example, let me know how many leaf nodes are present in this BST. Here 2 is a leaf node, 8 is a leaf node, and 25 are the leaf nodes. And I am taking, if I want to find the height of the level, that is root. So the maximum edges that are present in between the root node and the leaf node is called the height. If you took from here, it is 1 edge and 2 edges. If you look at from 8, it's 1, 2, 3. If you look at from 25, 1, 2. So the maximum number of edges are 3, and that's from the 8. So the height of this BST is 4. That is number of edges. Maximum number of edges are 3 plus 1. That gives you height of the binary search tree. 1, 2, 3, 4. So this is the height of the binary search tree. Let me explain this in terms of the code. Here I declared a function named find height of, and I given here node. Node is nothing but the root. Here node stands for the level. If node is null, no, not at all, because node has, there are some elements in the binary search tree. So node is not null. So we check. Here I declared some variable left height. LH is equals to find height of node dot left. That is, I am calling this function recursively in these both the cases. Now the node will be changed to node dot left. That is 4. Now it will becomes 4 and returns 4. Search tree we get 3, and from the entire right search tree we get 2. So in the return, maximum of left height and right height. The maximum of left height and right height is left height, that is 3. So 3 plus 1 is the maximum height of the BST. So here 4 is the maximum height that we have found.